Yesterday, we got introduction for digital control. Today, let us design a deadbeat controller for fourth order process. Let us review what we have seen yesterday. Digital controller. Digital control. In analog control, the controller output is 4 to 20 milliamps analog signal. Whereas in the digital controller, the output will be a digital output. The output is a mere number. If it is a 8-bit means it is 0 to 255. 16-bit means 0 to 64K. Like that, it is a digital output. But before getting into digital controller, suppose this is the controller output means this is analog output. Its range is this M of T, T. This is 4 to 20 milliamps signal. If it is digital means it is available only at sampling instances. Sampling instances. These are the digital controller output. If you convert this into 0 to 255 range, sometimes it may be 1.1, 5.4 or 7.2, like that you will get. Sorry, the number will be 4 milliamps corresponds to 0. 20 milliamps corresponds to 255 means you may get the numbers like this. But we have integer only. So we have to approximate this to 1. This has to be approximated to, suppose 5.6 means 6. 7.2 means approximated to 7. So this approximation is called quantization. Quantization. So quantization also a noise-like error. First, it will be converted into discrete value, discrete analog value. Then it will be converted into digital number by quantization. After quantization, it will be number from 0 to 255. By using that number, the controller gives periodic numbers. You cannot control the process by using that number because controller requires, the process requires analog signal to control it. Suppose this is the process. It requires the valve is here. The valve requires analog signal of 3 to 15 psi analog signal, not discrete signal. That's why before that I to P is there that converts 4 to 20 milliamps into 3 to 15 psi. Here the input is 4 to 20 milliamps. Here the output is 3 to 15 psi. If it is analog controller, no problem. If it is an analog controller, no problem. Here you will get set point. The feedback also analog signal, no problem. This is also 4 to 20 milliamps. Here error will be in the range 4 to 20 milliamps. So everything will be analog signal. But we want to replace this controller, analog controller, by a digital controller. So want to replace, that is called replace by digital controller. If you replace this by a digital controller, then the input must be a digital value. That's why here also set point also must be set point of K or Y set point of K. a digital value. The feedback also must be a digital value. That's why here also one ADC is placed. That's why here also you will get y of k, you will get, not y of t. Here it is y of t. Here it is y of t. Here it is called y star of t. It means sampled value. After that, one ADC will be there. That converts into y of k. So now you are getting in digital signal. So now you can put a digital controller. But the output of this digital controller cannot be directly used to drive the valve. DAC will be there. Then a hold circuit will be there. DAC will sample those values. Sample value is given. That's why I'm putting a switch here. DAC, digital to analog converter. If you give the digital to analog converter, again the signal will be like this. Before that, it is mere number. Mere number means m of k will be like this. Mere number. Mere number. It has no value. But if you give this mere number to DAC, it will give signals like this. Again, it is periodic signal. Again, it is periodic signal. It gives at one sampling period, it gives 2 volt. Let us assume at 0 to 5 volt output. Let us assume at the second sampling period, it gives 2.5 volt. At third sampling period, it gives 3 volt. Like that, let us assume. This corresponds to, this number corresponds to 2 volt. This number corresponds to 2.5 volt. This number corresponds to 3 volt. A number 0 to 255 or 0 to 65K number. That number is converted into voltage. Again, it is not analog signal. To convert this into analog signal, a hold circuit is there. That hold circuit will retain this 2 volt up to next sample value. So initially it is 0, then it raised to 2 and remain 2 up to next sampling period. At next sampling period, DAC output is 2.5 volt. Again, it raises to 2.5 and remain 2.5 till next sampling period. At next sampling period, it is 3 volt. After that, it remains 3 volt. The function of hold circuit is retain the DAC output for next value, till next value. If you buy a DAC at shop, it will be along with hold circuit. That's why you do not know about hold circuit. Always DAC alone is not available. It is available with hold circuit. That's why unknowingly you are using that DAC. Actually, a DAC along with hold circuit is available. But here the DAC, up to DAC, it is digital. Up to DAC, because DAC output also a digital signal. So up to this, it is digital. D of Z. This is D of Z. Let us assume that DAC model is 1. Then hold circuit, then process. Hold circuit only converts this into continuous signal. Then this is process. That's why in digital control system, process is not alone. It is with hold circuit. It is with hold circuit. That's why while considering digital control system, we should consider GP of S and H of S together. If it is in S domain, we can multiply these two. If it is in S domain, we can multiply H and S, because there is no sampler between this hold circuit and process. There is no sampler between hold circuit and process. That's why this is continuous signal. That's why we can multiply these two together in S domain. We can find H of Z. We can find GP of Z, but there is no use because we cannot multiply these two together. Because HGP of Z is not equal to H of Z, GP of Z. If you find separately and if you multiply, it is not equal. Here in S domain, we can multiply. That's why we have to find HGP of Z. HGP of Z only we have to find. So we have to cascade a hold circuit with the process. Then we have to obtain the mathematical model in Z domain, Z domain. So digital controller is in Z transform, Z transform domain. That's why we have to multiply the process GP of S by H of S. After that, we have to find Z transform. That we have seen yesterday. Now let us design a deadbeat controller D of Z for a first order process. Before designing D of Z, let us find the transfer derivation for D of Z. Here, what is input? Input is y of k. Here we are giving y set point of t is given. Y set point of k is, after sampling, it becomes y set point of k. Then it is given to a digital controller D of Z. Its sample values are given to DAC and hold circuit. The function of DAC is it converts analog value into digital value. That's why no need to consider that its transfer function is unity, let us assume. A hold circuit is there. After that, a process is there. Process is GP of S. Hold circuit is H of S. If you multiply these two together, then you will get HGP of S. You will get. The transfer function of zero order hold circuit is 1 minus e power minus Ts upon S. This is the transfer function of hold circuit. 1 minus e power minus Ts. T is the sampling period. If sampling period is 1, you will get 1 minus Z power minus 1 upon S you will get. Here, this transfer function is GP of S. In this case, let us assume that it is 1 by 3S plus 1. The transfer function GP of S equal to 1 by 3S plus 1. So this output is sampled and it is given to ADC. It is just converting analog value into digital one. Now it is given feedback. Here, this part is digital environment. This part is digital environment. Its transfer function is 1 because just converts analog into digital. So this part is digital part. This part is analog part. In between them, samplers are there. The Z transform of this part is Z transform of HGP of S. The Z transform of this part is T of Z. Therefore, the forward path transfer function is D of Z multiplied by HGP of Z. HGP of Z. The loop transfer function means this closed path we have to consider. We have to consider this closed path. If you consider the closed path, what and all there? D of Z, HGP of Z, HGP of Z multiplied by this is 1, this is 1, this is 1. That's all. Therefore, the closed loop transfer function y of Z upon y set point of Z equal to, because this is y of Z, here it is y set point of Z, here y of Z. Y of Z upon y set point of Z, forward path transfer function, that is D of Z, HGP of Z upon 1 plus, because negative feedback, that's why 1 plus loop transfer function is D of Z multiplied by HGP of Z. HGP of Z. That is closed loop transfer function. From this, we can find the D of Z. We can find the D of Z. What is Y of Z by Y set point of Z? Y of Z is the response. Y set point of Z is the input. Let us assume that we are giving a step input. Here, the response is like this. Let us assume if you discretize the sampling period is here means you will get these types of values. What is y of z by y set point of z? We have to find. If you know that, you can find d of z. If you know this, the ratio between output and input, you can find d of z. Now let us cross multiply this. What is we are having? Y of k, y of z upon y set point of z equal to d of z multiplied by h gp of z upon 1 plus d of z h gp of z. If you cross multiply, you will get y of z upon y set point of z plus d of z h gp of z multiplied by y of z upon y set point of z equal to g of z, d of z, h gp of z. Group d of z together, you will get, you can bring this to the right hand side. You can bring this to the right hand side. You will get y of z upon y set point of z equal to d of z in both cases. That's why d of z. Then this becomes negative in this side. HGP of z also you can take outside. The what and all remaining 1 minus y of z upon y set point of z. What you want? You want d of z. Therefore, d of z equal to y of z upon y set point of z. This part, left hand side, divided by HGP of z multiplied by 1 minus y of z by y set point of z multiplied by 1 by h gp of z. This is the digital controller. Whatever may be the digital controller, this is the expression. What is this? What is this? The given, the transfer function of the process, transfer function of process with hold circuit. What is y of z by y set point of z? Y of z is the output response. Output response. What is y set point? Input, reference or input. So if you know all these things, we can find d of z.